Hello YouTube. Today we will be talking about linear transformations. What they are, how we came up with them, why we need them, and of course some results and properties they have. So, first of all, let's try to make sense of how one might come up with this concept, the definition of linear transformations, which will be given after this. So, this is how I go about explaining it to myself. So we have two purely geometrical objects. We have a curve C and we have a line L. Now, both the curve and the line are two collections of points, but they obviously are not the same. They differ in their structure. I hope you agree with me on that this thingy, a line, is probably not equal to this thingy. That's a meaningful thing to say. And that they probably differ due to the structure arrangement of their points. So, observation. The line has a structure, and that structure is probably worthy of being called linear. Again, I hope you agree with me on this. Now, do we have an algebraic object? So a line is purely geometric. But do we have an algebraic object that can serve as a representation of the geometric line? And, well, yeah, we do. So here's a line, and if we want to translate it to the language of algebra, well, we have vector spaces, and a one-dimensional vector space is a line. So we can go between these two different context languages. So we got the line, and a very meaningful algebraic representation of that is the one-dimensional vector space. So, and now we can talk about higher dimensional vector spaces, so 2, 3, and above, and we get sort of a, well, generalization of this linear thingy via the language of algebra. That's why it's called linear algebra, I think. So now, the notion of vector space encodes, captures the structure of a line. A vector space is not just a collection of stuff, points, it is a collection of stuff with two rules, or operations of addition and scalar multiplication, that tell you how you can add and multiply stuff. The operations capture the structure. Thus, if we want a mapping, so if we want a function, a transformation, a mapping from one vector space to another vector space W, and we want our mapping to preserve the vector space, the linear structure of our original space, of the thingy we're transforming, then the mapping probably has to preserve the operations, so it can preserve that essential linear structure that we're after. Hence, why we have the following definition. So, what is a linear transformation? A linear transformation is, well, a function that maps V to some subset of W, such that these two properties hold. So, the if you take the sum of two vectors in your original space and you map them, that is equal to if you map the vectors separately and then added them in your other space. So addition is being preserved, and in the second case, the second property, we have that scalar multiplication is preserved. So if I take some vector and I scale it, stretch it, well, if I map that vector, it probably should be equal to, well, the original vector and then stretched the image of the original vector and then stretched in the other space. So this is what it means for something to be a linear transformation. So a very geometric example. So let's say we're in the plane and we have our one-dimensional vector space. So let T be a rotation. So we're gonna rotate everything in the plane by some angle. And it's just purely for illustrative purposes. So when I rotate everything here for some angle, so well, this line gets rotated to this line, and I mean they're not the same line, but what matters is that a line still remains a line after a rotation. So a line remains a line after rotating it. So here's a few more going into rotation to show that the properties hold. Again, purely just illustrative and pictorial. You're welcome to try and derive how a linear map of rotation would look like and show that this holds. But for example, if I take two vectors and I add them together and I get this vector, and now let's imagine I rotate this by like for some 45 degrees counterclockwise, well then I'll get something like this, and hopefully you can see that, yeah, if I take this vector and I rotate it by 45 degrees, I get this one, and that is indeed equal to, well, if I take this, rotate it over here, I get this, take this, so this whole thingy, and we rotate it, and it ends up like this. So the sum of those two vectors after they're rotated is equal to this, and this vector is equal to, if we took this vector and then rotated it by 45 degrees. So I hope you can see that this holds when dealing with rotations, and same goes when we scale our vectors, when we stretch or shrink them. So here's my vector x. Let's say I multiply it, I stretch it by some factor alpha, so I get this vector from here to here. Let's say I rotate again by 45 degrees, I get up something like this. Well, rotations don't change the length, so this vector has the same length as this, so when I scale it by alpha, I do get that this holds the two properties I'm after. So rotations, in this case, the rotation of the plane is a linear transformation. So I hope that provides enough motivation and clarification of the definition and why we're interested in these sorts of mappings, because they preserve the linear structure of our original vector space. Now we will go over some results and properties related to linear transformations. Now let's see how the basis of vector spaces and linear transformations interact, and yeah, go into some properties and results related to linear transformations. So here's a lovely consequence. If you have a linear map, so that takes your vector space V to some subset of W, which is again also a vector space, subspace. Well, a linear map of this sort is fully determined by its action on the basis B of our original vector space V. So what does this mean? What does it mean to say that it's fully determined by its action on the basis B? Well, let's take some arbitrary vector in V, and due to V having a basis, we can write V uniquely as this linear combination. Now, if I want to know what t does to my vector v, so I want to figure out where t sends it, well, let's just t of v is equal to, well, this, and now using the properties of t being a linear map, we have that, we can do the sum, and then we can pull out the scalars, so we get this result. So if I want to know what t of v is equal to, well, it turns out I just need to know, well, the scalars that were used to write v as a linear combination of the basis vectors, and I just need to know what t does to the basis vectors of v. For if I have that information, then I know what t of v will be equal to. So yeah, here's just that written out. So if you want to know how t acts on arbitrary v, we first figure out the action of t on the basis vectors, and then we have that any arbitrary vector in v, if we want to find out how t acts on it, well, then we just have this. So that's one thing. Another cute result. So let b be some basis of v. Take arbitrary w1 all the way to wn, so the same length, same amount of vectors as the vectors in the basis belonging to w. Then we can construct a linear map t that goes from b to w such that we can take the basis vectors of v, and we can make t so that t sends those basis vectors specifically to the vectors over here that we picked. So how to do that? Well, there's only really one way to do it. You have to define t to be this way. So if you take some vector v, again, it has a representation. So t of some arbitrary v, you define it to be this way. So you just, instead of the basis vectors, you keep the scalars in the linear combination of that vector the same, but you just change the basis vectors. So v1 here w1 all the way to vn, you put in wn. So this is the definition, the construction of this linear map. And now I will leave this for you as an exercise, as any good math teacher does. I was totally not lazy. Well, for example, so show that, well, this is a claim. We're claiming that we can construct such a linear map and that it is, well, it's a linear map and it does this. So, and I give you this definition claiming that this is the only way to do it. Well, your task is to show that, well, first of all, you have to show that this is a function. So again, read up on the definition of a function. You have to show that this thingy, if you have a thingy in your domain, it only gets mapped to one thingy, only one thingy. After you've shown that it's a function, you have to show that t is linear. So you have to show the properties from the definition, 1 and 2. And finally, you have to show that if I take some basis vector vj and I map it, that I do indeed get wj. So here's the definition. Here the thing is you have to show. I claim, I'm pretty sure that, trust me, all of these hold. So yeah, feel free to post in the comments. That would be it for basis and linear transformations. So the most important result is this, that the interplay between a base and a linear transformation, how knowing what the transformation does to the base encodes all of the information about the whole transformation. That's very important. So yeah, and now we're left with one final section and we'll be done for today. So final part of the video, the space of linear transformations, denoted, written this way. So let's get the definition out of the way. This thingy over here is just the set of all linear transformations from V to W, where of course V and W are always vector spaces. I hope that's clear from the context of us dealing with linear algebra. So you got your vector space V, you got your vector space W, and you have some mappings. Some of those mappings are linear, not all of them, and probably a small amount of those mappings are linear because it's quite a demand for a function to be linear. But yeah, you pick up all of those possible linear transformations and you put them in a box, and that's this thingy. That's the space of all linear transformations. Now, here's an interesting thingy, I think. So in the context of linear algebra, vector spaces are the algebraic objects we're dealing with. They're kind of like nouns, the nouns of linear algebra. And now linear transformations are, well, they're thingies that act upon the spaces and transform them into other things. They're kind of like verbs. So this set, the space of all linear transformations, the set of all linear transformation, is the set of all verbs from V to W. Well, it turns out that this thingy, if we define addition and multiplication, which we're going to do next, we can treat this with the corresponding operations as, well, a noun, also a vector space, which is kind of interesting. So take two linear transformations, T and S, and we define, addition of linear transformations to be like this. So T plus S of some vector, how this thingy is going to act upon this. Well, you act on V with T, get the result, and you act with S on V, you get a result, and you add up those thingies. And this is addition and scalar multiplication. So if you take some linear transformation and you want to scale that linear transformation, so, and you get a new linear transformation, well, then we have that this acting upon this, we define it to be equal to this. So act upon the vector first with t and then scale it. And now the consequences of these definitions is that this with addition and multiplication turns into a vector space, which I leave to you to show as an exercise. So you know you go through the definition of a vector space and check if all the properties hold. Now we will be introducing a sort of multiplication thingy. So how to achieve that? Usually when dealing with vectors, there really is no meaningful way to introduce any sort of like multiplication thingy between vectors. But in this case, when dealing with functions, there are pairs of linear functions where there is a sort of meaningful operation that might be worthy of the title of multiplication. So to show that, we'll need 3 vector spaces, and I will need a linear map T that goes from U to V, and I will need a linear map S that goes from V to W. And now we will define the product, the multiplication. So S times T. So what will it mean to multiply 2 linear transformations? We will just use the fact that these are functions and we will compose them. So what does composition mean? Well, T will take some U and map it to T of U. So over here in this space, and then S will take T of U and map it to S T of U in W. Well, so this thingy sends this here, this thingy sends this here. So I know this gets sent to this. So I can define this blue arrow to be a new linear transformation, S times T, that is defined by function composition. So U, gets mapped to this thingy. So I will just define S of T when acting upon U to send it to S of T of U. So that's composition. So this is how we're gonna introduce multiplication. So here's the definition. So let these 3 be vector spaces, take my 2 appropriate linear transformations, and we have that the composition of 2 functions is a functions, and it turns out the composition of 2 linear transformations is also a linear transformation. So when we compose these 2, this thingy still stays in the set of all linear transformations, which is good, which is if we were to multiply 2 numbers and not get a number out of it, then yeah, that multiplication probably wouldn't be that useful or meaningful. So we define S times T to be, again, just function composition. And some exercises for you to do to show that this thingy has some of the properties of multiplication. So first of all, show that S times T, again, function composition, the composition of 2 linear transformations is linear. And now 2, so S times T is called the product of S and T. And to motivate, well, the name of the product, verify that it has the following properties which are exhibited by a product. So again, think multiplication of numbers. So we have, associativity. So we can play around with the brackets when multiplying, when composing our linear transformations. There is an identity element. So there is a function I that just, well, does nothing. It's just, if you got some x, the identity just sends it to another x. It's like, yeah, like 1 times x is equal to x. So show that it's associative, show that there exists an identity element that behaves, like this. you multiply from the right side and you multiply from the left side, which is kind of important because the final observation will be that when you multiply two linear transformations, it's not commutative. So from which side you multiply, it does actually matter because commutativity does not hold, which we will show in a second. And again, the final property left is distributivity. So, if I have this sum times this linear transformation, again from the left side, then this is equal to that. And if I have this from the right side, then this is equal to this. Again, sides matter due to this. This does not always hold. They're not commutative in general. For an example, to give a counterexample, take P, let it be a polynomial with coefficients in the real numbers. And now, one linear transformation I will perform on P is I will take the derivative. If you know what the derivative is, great. If not, the only thing you need to know is that it's a linear transformation. So I take the derivative of my polynomial and I get this. And now to this, I will apply another linear transformation. I will multiply this by x squared, which it turns out is a linear transformation. Again, feel free to verify all of this. So we get this. So this is one product of two linear transformations. So this is s times t. I do t first, I get the result, and then to the result I apply s. So this is the result of s times t. Now let's change up the order. So let's do s first. So let's multiply by x squared. We get this, and let's take the derivative then. Well, then we get this. Again, if you know what a derivative is, great. If not, just trust me, bro. So you get this. And these two thingies are in general, yeah, they're not equal. So s times t is not in general equal to t of s. So this product, this multiplication, in contrast to the multiplication of real numbers, which is commutative. Well, this is not commutative. It is not that nice of a multiplication, but still it exhibits some very nice-ish multiplication properties. Again, associativity, identity element, and distributivity, still pretty nice. So yeah, that would be it for today. Linear transformations, the why, the how, a few results, and yeah, we introduced the space of linear transformations and turned it into a vector space. So yeah, hope you learned something. Have a good one.